Okay, now we're going to talk about interrupts. And now that you've flashed a few lights and set the PLL, this is probably the next most important topic. And I'm going to go over, there are two approaches you can take on interrupts, two classical approaches. And we offer you whichever you like. And in the end, though, the example I'm going to give you is 1 millisecond task scheduler that also generates a 2 millisecond task. And you can take it from there. You also see kind of the boilerplate for how we can generate additional interrupts for other peripherals, because we're only going to have two interrupts used in the example we're leading up to. One's the PIT, and one is a software-generated interrupt. And so as you have other peripherals that you want to have an interrupt request, you'll have to enable that interrupt request and come up with your own interrupt service routine, and I'll show you how to plug that in. All right. First of all, distinction. There are core interrupts, and there are interrupts from, say, peripherals. And so the core interrupts are things like machine check, like that's something bad. It just sounds bad. It is bad, and you probably can't recover. There could be a data storage. You went to write to an area which is not legal. Instruction, you're executing the wrong place. Alignment problem or program. A system call is something you can do yourself. These are relatively infrequent interrupts, though, at the core, but they are core interrupts. But there is one real common core interrupt, and that is an interrupt external to the core. So the core has this external input for interrupts. We also call it exceptions, but for all practical purposes, interrupts and exceptions are the same thing. This external input, though, for interrupts is connected to the interrupt controller, and all those peripherals that have dozens, maybe hundreds of interrupt requests. Those are all managed by the interrupt controller, and they can funnel it into one interrupt vector or a common one or individual ones that we'll see in a moment. Okay, so this is probably the key thing to understand about interrupts. What happens when an interrupt is recognized? Okay, hardware, number one, does a context switch. It stores the address of the next instruction, usually the next, or the one causing the interrupt. And normally it's just the next instruction. If something bad happened, then you could store the address of the offending instruction. And that's stored into a special purpose register called Save and Restore Register 0, SRR0. And then it also stores the machine state, which is from the machine state register, very original. And that's stored in a different save and restore register, number 1, SRR1. So it's saved where, an address, and it's saved the state. Now it's going to change the instruction pointer, and it's going to change the state. And the instruction pointer will be changed to a vector for the interrupt, and the machine state will basically disable further interrupts, except for maybe machine check enable. But in general, it's kind of like putting Windows into a safe mode. Oh, let me just get rid of everything I can so I can manage where I'm at. And then you enable interrupts again when you are ready, if you want to, during the interrupt routine. So that's what the hardware does. As the software interrupt handler, you will execute the code, which will include a prologue to save registers, a interrupt service routine to do your stuff, and an epilogue to restore registers. And then the last instruction is return from interrupt, RFI. And this will restore the machine state, and this will restore the instruction pointer from these two registers. Anybody want to nest interrupts? Recognize, because we're going to have priorities for these peripherals. You do? Okay. Someone in the back row does. So, if you want to nest interrupts, you have to re-enable interrupts somewhere during your interrupt handler. So before you do that, before you re-enable interrupts, during this software interrupt handler, what should you save first? Do 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 do. Anybody know? I want to take a guess.
Enable all interrupts.
Well, you enable all interrupts, but if another interrupt comes along, it will write to SRR0 and write to SRR1. So what you want to save is SRR0 and SRR1 before you re-enable interrupts. Otherwise, your previous machine state will be overwritten. So that's the first thing you do. As soon as you, in your handler, have backed up this prior machine state of SRR1, SRR0 on the stack, then you can re-enable interrupts. And that's what the code does for the interrupt handler. It saves only what's necessary, so for minimum time, then re-enable interrupts so a higher priority one can be recognized. Okay, so let's talk about vectors. You know, so I said the instruction pointer has changed, or program counter, same thing. And where does it go? Well, every interrupt, you can see the interrupt types listed here, and the one that we'll be using 99% of the time has a number, 0, and we call it 0 through 4 through 15, and there is an offset for each interrupt type. And it's basically the interrupt number times 10 hex, you know, times 16. So this offset will be used to go to an address that is a combination of the upper bits from an interrupt vector prefix register plus that offset. So in this case, I'm showing here IVPR plus an offset of 40. But this is true with all the core interrupts. The vector will be to an offset of part of the bits will come from the interrupt vector prefix register, the others will come from this physical offset. But the interrupt controller has another option. I'm going to give you two ways to generate interrupts, and I want to ask which one you want to use. One is you've got, let's say, 50 peripherals that can cause an interrupt. I can give each peripheral its own unique vector. So the PWM generates interrupt, it goes to location X. And there I save registers, do my interrupt service routine, restore registers, return. And SPI generates interrupt, it goes to interrupt vector Y. And so there now I have different code to save registers and do my interrupt service routine, restore registers, and return. And same thing for other peripherals. So in that case, hardware will give you a unique vector every time for every different interrupt. So hardware vectors you. The other approach is you have one vector for all these peripherals, and you go to that one vector and you save registers. So you have this common prologue, and now you read a number to see what was the interrupt vector, who did it. And you use that number to index into a table of interrupt service routines to execute, and you go there to interrupt service routine, you come back to a common epilogue to restore registers and routines. So what are pros and cons of software vectoring you, in other words, finding the vector, or hardware doing it for you?
Software seems like it takes up much less space.
Software takes up much less space. Why?
Because you vectorize it and then you use pointers to go over instead of having like physical.
Yeah, you don't have multiple prologues and epilogues. If you have 50 routines, you would have 50 prologues and epilogues. So it's wasted space. What's the advantage of a hardware vector, though? Faster, yes. How much faster? Well, it might take you a half a microsecond or a microsecond to save the registers. And we haven't talked about what registers yet. That's coming up. And I've measured and you can measure, because I give you an example for both software and hardware vector, and put a breakpoint at the first ISR instruction and read the pit. And you can use that because when pit reaches 0, I get an interrupt, and you can measure the difference. I think you'll find the difference is a few percent in time. Software is a little easier because you don't have to cut and paste all those assembly language instructions. I think, also, and those section maps and all that. I'll show you the software. So, okay, now, so we have software vector mode and hardware vector mode, as we call it. And there's a bit you set in the interrupt controller. What do you want? So let's just look at how it works. We're going to start with software vector mode. I'm going to have a interrupt occur, interrupt N. So I go to this common address for software vector mode, and I save registers on the stack. And there's one other housekeeping. I have to read a register to tell me who did it. Who's the guy? Who caused the interrupt? And oh, number 41, because the IAC register tells me. Thank you very much. So I store number 41 for right now. Then I go into this table of interrupt service routines, addresses, get an address for vector 41, and then I branch to that ISR at the end of the, which is just a C call. So it's just a C function, and the return of the C function comes right back to where I was, and now I restore registers. So in this prologue, I'm going to, if I'm going to nest interrupts, I'm going to save the SRR0 and SRR1. That's a prior machine state, like we mentioned. And then I must read this interrupt vector to find out who did it. Then I can now enable interrupts again. So that's software vector mode. Hardware vector mode gives a unique address for each of these, maybe hundreds of interrupt potentially. And so I'm going to have a table. And the table is the same prefix, this interrupt vector prefix, plus 800 hex times 4 times the interrupt number. So it's just a little formula here. And so this gets me into a branch table, and I branch to these different handlers. And there's a prologue, interrupt service routine, and epilogue. So here's, it's very apparent. I've got all these prologues. This does take up more space.